Hello and welcome to today's session. Today we'll be doing differential calculus. So I'm gonna firstly take you through a recap of differential calculus, but most importantly we'll be focusing on the things that we can apply when we're dealing with cubic functions. Okay, so I'm gonna give you a basic recap of differential calculus, and then we'll quickly tackle a problem which involves cubic functions. All right, so first thing first, in the previous grades, that would be grade 11 and grade 10, you learned that a straight line, we can find the gradient of that line, basically the slope of that line, how the function is increasing or decreasing. Okay, how we do this, we simply say this is change in y over change in x. All right, so but now when we go to higher order functions such as hyperbolas and parabolas and cubic functions, we cannot simply do that to get the gradient of that function. So we need what we call a differential calculus to help us to find the gradient of that function. Now suppose we have a function like that. Let's say that is some cubic function. We want the gradient at that specific point. Okay, so we know that the gradient is not the same now as everywhere as like a straight line. So but if we want the gradient at that specific point, this is how we're going to do it. Okay, so suppose this is function y, which is simply f of x. Okay, so if we want the gradient there, we first have to differentiate the function. So we first have to find dy over dx, which is the same thing as differentiating f of x. Okay, so this is the derivative of f. All right, so when we differentiate a function like that, we get what we call a gradient function. So now that basically is a function that gives you the gradient of f at any point. If you need a gradient at point -2, you simply substitute -2 into that function that we call a derivative, then it's going to give you a gradient. All right, so now that we are able to find the gradient using the derivative of any function, so one may ask, but how do I actually do that? All right, so given now a polynomial function, let's say you're given f of x, which is basically ax to the n. Remember now your a is a constant and your n is a constant. Both of them are non-zero constants. If now we're looking for derivative of f, we will simply say now this as it is. The rule says for polynomial functions such as this one, the rule says you take the exponent, you multiply it by the coefficient. So now we're going to have n multiplied by a, and then we still have x, and then we subtract 1 from that exponent. So we're going to have n minus 1. So basically that's how we find a derivative of a polynomial function. We can have a lot of variables here, as I'm going to show in this example. Now let's suppose that our f of x is actually a known function. Let's say this is 5x squared, or rather x cubed, plus 2x squared, plus 6x, and then minus 7. Okay, so if we're looking for the derivative of f, we're going to say, we're following the same rule that I just explained. We're going to say this is 3 multiplied by 5. So you're going to have 3 by 5. Okay, and then you still have x, and then that's to the power of 3. We subtract 1 from it. Okay, now we go to the second term, which is plus, and then this by that is going to be 2 by 2 x to the 2 minus 1. Okay, plus the next term is going to be 6. Okay, so it's going to be x first, and then what's the exponent there is 1, so it's going to be 6 multiplied by 1, and then x to the power of 1 minus 1. Okay, and then the next one, which is important to notice here, is that basically we have what we call x to the power of 0, because anything to the power of 0 is 1. So now when you take that 0, say 0 by 7, it's going to give you what? 0, right? So we're going to 7 times 0, and then we're going to be left with x to the power of 0 minus 1. Now we can see that this is simply 15x squared plus 4x, right? And then now plus 6, and then minus 0. Okay, so now what we're learning here is whenever we have a constant, the derivative of that constant is always 0. You don't have to do this. I just did this to make sure that you understand where the 0 is coming from. All right, so now with this, basically given any function, a polynomial function, that's a parabola, a hyperbola as well, we can simplify it into a polynomial such that we can take the derivative of that function and then find the gradient at any point where we want it. So we'll see why this is important, as I'm going to explain when we do our next question. All right, without any waste of time, let's just jump into our problem and see how we can apply what we just learned here. Okay, so our problem for the day is as follows. We're given the statement that is read as follows. The graph of f, which is f of x, is equivalent to x cubed plus bx squared plus cx minus 4 is drawn below. A and B, that's A and B, are the turning points of f. We can see that's the graph is turning there, turning there. So that's a local maximum, local minimum. All right. So the x-intercept and the y-intercept are clearly indicated here on the sketch. So that's the y-intercept, and then that's the x-intercept there. We are given the coordinates for both intercepts and also for both turning points. However, we don't know what the values are for that specific turning point, which is at point B. All right, so the first question says, show that the values of B and C are -6 and 9 respectively. Okay, so B and C are actually there in the equation. So as we can see, our equation is not complete. So we need to find those values to complete our equation. All right, the first thing first, we know that a cubic function has a nature of this form. So we have ax cubed plus bx squared plus cx plus d. All right, so where d is your y-intercept, okay, in this case it's -4, which is at -4 there. All right, and then the other constant or the other coefficient that we're given is a. Okay, so we can see a is equivalent to 1. Why am I saying that? Because that's the coefficient of x cubed there. All right, so but we're only interested in finding b and c because this is already given, and then I can say d is -4. Okay, so this is 3 marks. So all right, let's be strategic about this so that we don't spend a lot of time on this because it's only 3 marks. So this is how we were doing this. So remember, a cubic function has how many roots? It has 3 roots. Okay, so you can write a cubic function as a into x minus x1 into x minus x2 into x minus x3. Okay, what are these x1, x2, and x3? These are the roots of your cubic function. All right, so if this was a parabola, we're gonna only have 2 roots, because it's a cubic, it has 3 roots. Okay, but looking at the sketch here, one can say, but there are only 2 roots there. Looking at it, okay, the same thing as happens when you have, let me quickly go back to a parabola. We know a parabola generally has 2 roots. So when you have a parabola that does something like that, you see, so one can then again say, but there's only 1 root there. That would be incorrect, because the reason is the root there are 2 of them, they're just repeated at 1 point. Okay, so that's the same thing here. So that means 1 root is also repeated there. So this is how do we know which one? Okay, the only time where a root is repeated is if it happens when there is a turning point. Okay, so as we can see also for a parabola, that was a turning point there and also an x-intercept, hence the root was repeated. So now we can see here, going back to our cubic function, that point A is a turning point. We're told 10 is a turning point, and also an x-intercept. That means the root there is repeated. Okay, so that means our x1 is 1, our x2 is also 1 because it's repeated there, and then our x3 would be 4, which is that one there. All right, so now we can go back into the equation. Remember, we know what a is, right? We know what a is. A is 1 because we can see from that. All right, so taking this further, so now we're going to have f of x is equivalent to, that's your a is 1, so it's going to be just 1, and then we'll have x minus 1, right? And then x minus 1, okay? And then we'll have again x minus 4. So these are the repeated roots at a turning point there. Okay, so now we have to multiply everything out. So the 1 is just 1, it doesn't make any difference here, so we'll have to multiply this one first. So x multiplied by x will have x squared. Alright, x multiplied by minus 1 will have minus x, and then also this minus 1 by x will be minus x, so we have minus x, so this will give us minus 2x, and then minus 1 by minus 1, that's plus 1. Okay, so now we have x minus 4. Alright, so now we need to multiply out throughout, so we'll start with this. X multiplied by x squared, that gives us x to the power of 3. X multiplied by minus 2x, that gives us minus 2x squared. And then x multiplied by 1, that gives us plus x. Okay, so now minus 4 multiplied by x squared. So now we have minus 4x squared. Minus 4 multiplied by minus 2x, that's plus 8x. And then minus 4 plus 1, that's minus 4. Sorry, minus 4 multiplied by plus 1. Okay, so now we need to add the like terms together, which we can see anything to the power of 3 is only x cubed. So anything to the power of 2, we have minus 2x squared and minus 4x squared. When we add the 2, we get minus 6x squared. Okay, and then for x, anything to the power of 1, we have 1x plus 8x, so that's basically 9x. And then the minus 4 is just alone minus 4. Alright, so now we have our cubic function like that. So now we need to compare it to what we were given before there. Okay, so we know that our a is 1, if with that we could find, and then now our b as the coefficient of x squared, we can see here it's minus 6. Now your c as a coefficient of x, we can see here c is positive 9. So now we have shown that both b and c are minus 6 and 9 respectively. So that's how we solve such a problem, making use of the roots which are given to you. If the function did not have like the repeated roots, maybe it was just a normal cubic function crossing the x-intercept 3 times, then we're going to do the same thing where roots are not repeated. Alright, so the next question, which is number 2, says determine the coordinates of b. Alright, so what is b? B is a turning point or a local minimum. Okay, so you can see the graph is turning there, it's going up. It was initially going down, now it's turning going up, or it's a local minimum. So this is a minimum point, it's at its lowest, but a locally, right? So it's a local minimum. By local, I mean this is not generally the lowest point that the graph has, because we can see it's going down this way, but this side it is the minimum. So that's why we say it's a local minimum, looking at just the local points. Okay, so in other words, just a local minimum or a turning point. All right, so now we need to determine the coordinates of b, which is a turning point. So how do we do that? The first thing is we need to understand what happens at a turning point. So as I was talking about in the introduction of this video, we're talking about the gradient. So the gradient of a function at a turning point is always 0. You can see here the gradient is negative because the function is going down. Here the gradient is positive because the function is going up. So for you to move from negative to positive, you must cross 0. You cannot jump 0. So this is what's happening here. That's where the gradient is 0. Okay, so that's why we need to apply calculus so that we can find those turning points. All right, so remember we have found out that our f of x is x cubed minus 6x squared plus 9x minus 4. So if we want to find where the gradient is going to be 0, because we know the gradient is 0 there, how do we do that? The first thing we need to find the gradient function. How do we do that? We find the derivative. So the derivative of f is, as I've explained, 3 by 1, that's 3x squared, right? Okay, 6 by 2, that's going to be minus 12x, and then this is just going to be plus 9. Okay, I'm just following the rules that we spoke about in the introduction of this video. All right, so that's the gradient function or the derivative. So we want to know, where is this gradient 0, because we know this is 0, so it has to be 0 at the turning points. It has to be 0 there and there. So what should we do next? We say let f of x be 0, because we know it has to be 0 at the turning points. And then, but we're looking for the x values that make this 0, then that x value has to be that value there. So now we're saying that means 3x squared minus 12x plus 9 is equivalent to 0. We can divide by 3. We're getting x squared minus 4x, and then plus 3 is equivalent to 0. Can we factorize this? Of course we can. So this is x and x. We can 3 and 1. Right, so this is going to be minus minus. Okay, because minus 3x minus x, let's give us minus 4x there. And then when you multiply them, still get that. So now your x is 1 or your x is 3. We can see the 1 there has to be that 1 because we know that's a turning point. Okay, so this confirms that we're on the right track. All right, so now we know that x value is 3 there. How do we find the y? Okay, but this is a point on the function f. If we know the x value, we can simply substitute that x value into that function. It's going to give us the y value. All right, so now we're going to simply say f of 3, which is going to be 3 cubed minus 6 into 3 squared plus 9 into 3 minus 4. Let me quickly punch that into my calculator and see what am I getting. All right, so this gives me f of 3 is equivalent to minus 4. We can see that this is negative. It's on a negative side there. All right, so then we're on the right track as well. So now we're going to say, therefore, point B is actually 3 and minus 4. Okay. Okay, so the next question, they're asking for which values of x is the graph f increasing. Okay, so we know when a function is increasing, it's going up, looking at it from left to right. Okay, so left to right, it's going up. It's going up. So we already know it's those that it's from negative infinity to that point, and also from that point to positive infinity. We can easily see that from the graph. If you don't have the graph, then you'll have to go to that derivative function you found, and then say that function is greater than 0, then solve that inequality. But because we have a graph now, it makes it simple. So we can say, we know it's increasing here. So you can say now, x is an element of negative infinity up until that point there, which is 1. And that point is excluded because at that point, the function is not increasing or decreasing. The gradient is 0, which is what we spoke about. Okay, and then or again we can say x is an element of, from the turning point there, which was 3 to infinity. Okay, so the last question says, show that the point of inflation lies on the straight line G that passes through C and D. We have a straight line G there, passes through C and D. So, okay, as a side note, we have 2 points there. We are good enough to find that equation with a straight line. Okay, but now let's look at on the other side of information. We're given that there's a point of inflection. So a point of inflection, quickly, is a point on a cubic function where a cubic function changes concavity. Okay, what do I mean by that? So we can see here your function is concave down. Basically, it's looking down. It's a sad face. Okay, you see that? Okay, and then after some time, now your function is generally now a smiley face. Can you see now it's looking up and smiling? So there's a point somewhere there where it actually changes from concave up to concave down, or concave down to up. So that point is a point of inflection. Okay, so we're interested in finding that point. So how do we find that point? So we find that point by taking the second derivative of f of x. So remember, we had f of x and we found the first derivative, which we found to be 3x squared minus 12x plus 9. Okay, so now when you take the second derivative of f, what we have derived, you actually derive it again. So this is f of x, you derive it, first derivative you get that, second derivative you derive it again. So you will derive this again to get the second derivative, which will give you, that's gonna give you 6x, remember, 2 by 3, which is 6, and then subtract 1 there, left with just 1, and then minus there, which is gonna be 12, okay? Because the 1 there multiplied by 12 is just 12, and then the x is raised to the power of 1 minus 1, which is 0. So anything to the power of 0 is 1. Okay, so at a point of inflation, your second derivative is 0. Okay, so we do the same thing. Let the second derivative equals to 0, which means we have 6x minus 12 equals to 0. We have 6x, which is equal to 12. So your x basically is the same thing as 12 divided by 6, which is 2. Okay, so they're telling us the point of inflation is somewhere there at 2, but now the question says show that that point lies on a straight line. So now we know the point there, we know the x value, we just need to find the equivalent y value. So that means we need to find f of 2. Okay, so you can quickly punch that into the calculator, and then let's see what we're getting. And then we're getting that to be minus 2. So the point of inflation is actually 2 and minus 2. So we need to show now, that this point actually lies on a straight line. So at this point, there are two ways of approaching this. You can find the equation of this straight line, and then when you substitute 2, you must get negative 2, because that would be where they meet there. Okay, another way of doing that is that, so remember now we know at this point that this is actually 2 and minus 2. Okay, another way is actually finding the gradient between this point and that point, and also finding the gradient between that point and that point. Those two gradients should be the same. So I'm gonna go for this method of finding the two gradients because it's an easier one. They are both relatively easy to do, but this is a quicker one. So I'm gonna say gradient 1 is gonna be change in y over change in x. Okay, so now change in y will be y2 minus y1 over x2 minus x1. All right, so I'm gonna start. Let's take this to be x2 y2 and then x1 y1. So this is gonna be minus 2 minus 4, and then we're gonna have here 2 minus 0. So now we have minus 2 plus 4, which is 2 over 2, and that's 1. So that's our gradient. So if I take the same gradient from here to here, it should be the same gradient if that point is on a straight line. Okay, so the second gradient, I call it gradient 2. All right, so this is how we do it as well, changing y over changing x. Okay, which is y2 minus y1 over x2 minus x1. Okay, so I'll take this as well to be x2, y2, x1, y1. Right, so now we have 0 minus 2 over 4 minus 2. Okay, so that's basically becomes 0 plus 2 over 2, which is 1. Okay, so now gradient 1 is actually equivalent to gradient 2. What does this mean? So this means that this line has to be, this point has to be on this line. Okay, because we know this is a straight line, and then the gradient here is the same as that gradient. All right, so that's one method. The other method is to actually find the equation of the straight line. All right, in a sense that y minus y1 is equivalent to m into x minus x1. Okay, so we already know that the gradient is actually 1, so we can say this is simply 1. Okay, so let's say 1 minus, let's use this point d there, so your y is 0, so that's 0, and then we have x minus 4. All right, so now we have y is equivalent to x minus 4. That's the equation of the straight line. So if I put x equals to 2 here, I must get minus 2 there. Let's see. So y, when x is equals to 2, it's actually 2 minus 4, which gives me minus 2. Right, so now these are the two ways of proving that this point lies on that function, g, which is a straight line. All right, so now just a quick recap. We looked at calculus. We understand that finding the gradient of a function, a higher order function such as parabola, cubic functions, we cannot simply find it this way. We need to differentiate that function. Okay, so we did that. We learned how to differentiate our polynomial functions, and then we did that. We also applied that information knowing that the derivative of a function at the turning point is actually 0, and also we know that the second derivative of a function at a point of inflection is actually 0 as well. So we use that information to actually solve and find the coordinates of cubic function. So this is how we are applying calculus into cubic functions to be able to solve for turning points and point of inflection and so forth. So this concludes our lesson for today, and yeah, I hope you at this point you can see things from a different perspective on how we can apply calculus to make our lives a bit easier into solving cubic functions. All right, thank you for tuning in, and I hope you've enjoyed our lesson. Bye bye.